Good morning, guys. Hello, and maybe good afternoon or maybe even good evening for wherever you are. Zubul here again, and today I'm not going to code. I'm not going to talk about any particular code today or any project. Today, I would like to discuss the main purpose of this channel with you guys. As you could remember, I started this channel with a goal of sharing my challenge of becoming a software engineer. I think that started back then in June last year, 2018, and very soon it will be 1 year since I set up myself that goal. Initially, I set that goal for 2 years, so of becoming a computer software engineer, and in the middle of that, just say, after I started it, I realized something. As I started learning, I realized that it shouldn't be a software engineering student, but instead computer engineering student. And the reason is simple, and that's one of the reasons why I'm making this video today. It's a way for me to give you a report of how things are going and what I've discovered so far, and what I think is important for any software engineer out there to know before he even qualifies himself as a software engineer. So the first reason why I had to change the channel name from software engineering student to computer engineering student is I realized that software engineering is just a subset of the whole computer engineering, and the computer engineering covers not only the software part of it, but it also covers the architecture and the design of the computer itself. And what I think is very important to any software engineer or software developer, whosoever it is, to know. So it is very important for you to really know what a computer is. You know, until recently, I was like, oh yeah, software development and all this, and then I realized, like, honestly, I had no idea of what I was doing. So there are some things as a software developer or as a software engineer, if you don't know, it's like you are working blindly. You are doing anything blindly, and it is so funny. It is just so funny that especially we, the self-trained, the self-learned software developers, we are blinder than anybody else, because what we do, we have no idea what we are why we are doing it. So we are used to try and failures, and then we try, you fail, you see the result and all this. So based on that, we call ourselves developers. I think there's something very important everybody should know first before even starts learning programming. I think the main thing is to know why programming exists. Why do we program computers? It is very important to me, and that's it's part of the reasons why I had to change the channel's name to computer engineering, because as I was trying to understand the software, I was feeling myself dragged down to the hardware. I was feeling myself dragged down to the metal of the computer in order to understand what the software actually is. It's just surprising if you ask so many developers today, how is your software you write executed inside a computer? Honestly, few of us will be able to explain that. So how do you write a computer program? How do you write a good computer program if you don't even know how the computer runs your program? So this blindness, so it's like working without knowing where you are going. So I decided to focus a bit on the hardware part of the computer a bit, try to spend some time there, trying to understand how that goes. So far, it wasn't that bad. I had to do a bit of electronics. It's not easy at all. It's not easy at all, because electronics is not just soft and so easily manipulable. So you really have to practice a lot. Until just, I think this week I was able to use a 555 timer to build a clock. You can imagine all this while. So, and depending on where you are, it might be even impossible to get the little component or little parts of it, and then experiment with your electronics. So far, what I think is, as a software developer, you should ask yourself these questions. Why do I write a program? Where is my program executed? How does the computer take my program, and how does it transform it into a function or an activity inside itself? So if you want to understand that, you go deep into the computer system, learn how the the processor is built, and then how the process, how from the circuit, the processor circuit, how do we come up with assembly languages, and from the machine language, from the machine language, how do we come up with assembly language? And these are the points today. Even talking of this assembly language, when you meet people, when you let them know, will you learn assembly? No, most people will tell you, no, this is for the old thing, this is old time, and all this. Funny, this is not old time, it is still there, it's always there. And I think it is important, it's even a must. If I have to open a school and let people come and learn programming there, you must learn assembly language. There's nothing you can do, because understanding assembly means you understand the microprocessor very well. So it is key for anybody who is a software developer out there to reconsider what he is doing. But it is not necessarily a must. So many people are geniuses that they can even start with any language and they are just good about it. But one thing is sure, if you write a program today in Python, you are so good in Python, you are so good in Ruby on Rails, you are so good in JavaScript. Now you write a program. If I ask you, for instance, how long do you think your processor will take to execute that program? Could you easily determine that? I'm not sure. I'm not sure. You can't, because you might tell me it will depend on the computer on which you are or whatever you are. So many things you will tell me, but honestly, if you were to use assembly, if you knew how the processor works, if you had the code, the instruction set from a microprocessor you are using, and you write that program using assembly, it will be very easy for you to determine that, because you know each instruction, how long each instruction from your processor takes. It will be very easy, and that makes sense. And until you know those details, until you understand that principle behind the microprocessor, I don't think you will ever be able to write some kind of software. So this is the note I have for my fellow developers, and this is what I have discovered so far. So I'm opening this screen just to show you a bit what I think is going on behind the computer there. So the whole thing happens between the microprocessor. Let me take this. So the processor and then the memory RAM. Mostly this is where the whole thing happens. So the processor, I'll probably make videos explaining each part of this CPU. So let's call it a CPU, okay? Let's just call it CPU. And the CPU control processing center, or central processing unit, okay? The central processing unit. In the central processing unit, we have two main units that are very important, that are the arithmetic logic unit. Okay, it does the arithmetic and the logic calculations. We'll come back to those details on further videos. This is just a summary of what I think is going on there, and why, especially understand through this, you should understand why assembly language is born. Why do we need assembly language? What is the difference between assembly language and the machine code? Okay, so you have the arithmetic logic unit, then you have the program counter, let's say PC. So another model called the program counter. So all this set together becomes the central processing unit, because actually that's where the processing goes. So what it happens is, I will not mention too much about the clock part because it's very important, but just consider that the clock is actually kind of giving orders to the microprocessor to do something at some few seconds, like just say, okay, do it. So every time the clock says do it, so the processor, actually the CPU, does an activity. Every time the clock says do it, the processor does an activity. So you can imagine, the faster the clock says do it, the faster the processor can calculate. So understand the clock is just like that for now. And that's why when you buy a computer, you are concerned about the speed of your processor, which is sometimes I have a 2 gigahertz processor, I have 1 gigahertz, I have 1.5, you know this. So this is basically what it means, and you should know this in terms of frequencies. Okay, so 1 gigahertz, let's say 1 megahertz processor, it means the clock gives the order of I think MGH or MHZ anyway. So it's like the clock says, okay, 1 million times per second in terms of 1 megahertz. 1 million times the clock will say to the CPU, do it 1 million times in a second of your watch. So this is very, very fast. So you can imagine 1 gigahertz of processor. So that's why your computer can really process so many things. So what happens is this now. So every time the clock says to the CPU to do something, the arithmetic logic and the arithmetic and logic unit will actually take two values. Okay, so let's say two operand A and operand B. So usually what it does is probably calculate the sum of it, either the sum of it or the multiplication of it or the subtraction or the division, whatever arithmetic it might happen. And the circuits are built to do all those things, and certainly we'll come into that. So it does this calculation here, and while it does this calculation, there are other internal memories that are inside the CPU that are usually called registers or accumulators. So those memories, let me call them, let me just draw them like that. Okay, right. So let me say we have these memories like this. Let me just even use one, and I'll call it accumulator AC. Let me just make it AC like this. So what the processor will usually do is, whatever value it calculates here, like the sum of this, store it a bit in the accumulator here, keep it temporarily here. So let me call it store. Okay, store it temporarily in the accumulator. From the accumulator, now go inside the memory. You know, the memory RAM actually is one of the best and the most complex part of any computer. That actually, the memory is what determines all this programming stuff, because the reason is this: the memory is actually a set of circuits that can store one bit. There are small electronic circuits that can latch. This is an electronic term, which means when you actually set those small circuits and you connect them to the power, they can give you can see a result. Let's assume you have a small light that is connected to that circuit, so that light will be on. So even if you unplug it for some time, you unplug it, that light will still be on, which we call the circuit has a memory. So when we combine these small circuits that have one memory, we can combine like as many as we want. So if you combine like 4, so you have a memory of 4 bits. So the memory is actually a set of those memories. So sometimes you see a memory of 8 bits. That's when you say your computer is an 8-bit something or whatever, or you see 16-bit or 64-bit. So that's why the memory size is actually important, because you can imagine, since they are actually binary binary information, if you have, let's say, 4 bits, that's 2 raised to power 4 possibilities of encoding data. So there are many ways. The larger the weight, the larger actually the number of bits the RAM can have in a row, the bigger the data we can encode with that memory. So this is how you need to understand it. So if you have a memory that can store such rows of information, it is important to locate the information. So for each row, we need to know where is the rows located. So that's what is called the address. So we need the address of each row. Now once we find the address, we need to enter the data itself. So you find the address, you enter the data. You find the address, you enter the data. Either you enter it or even you read the data. So you can even read the data. Either we enter it or we read it. Okay. So as the CPU does this work, whatever information you enter, either the information comes from an accumulator or from another input, which is the keyboard or maybe whatever it is, or another registry or another memory somewhere, wherever you take the information from, you enter it in the memory, the program counter will always have some kind of arrow here trying to count. We'll come on these details and probably further videos. So the program counter will always go through the memory RAMs, each one of the addresses, find the address A, and read whatever information is in there. Take the address B, address C, address D, and so on, and go through all these addresses and try to find whatever instruction is there. So whenever it finds the instruction, it takes the instruction probably to the accumulator or whatever whatever part of the memory. The arithmetic logic does the calculation, saves the data inside another accumulator or another registry, then goes back to the next instruction to find whatever is there and follows the instruction. Whatever the instruction says there, that's what it will do. And that's important to us, because I'm using the example of the memory here, because this goes very complex and deeper, especially when you start having more registries. Okay, so in time, what happens is the data we are storing, or the data the program counter is taking, it has, let's say, two parts of it. If you assume it's 8-bit data, so I'll have 4 bits in the first section here, then 4 bits here as well. So all makes up an 8-bit data set. So what we do is we consider that, okay, the first 4 bits will be used to give the instruction to the CPU, which is, let me say, instruction I. So this encodes the instruction, which is, if we consider 0, 0, 0, 1, whenever the computer sees this instruction, it goes to a particular circuit that is designed to respond to this particular code. And that circuit probably will say, okay, go and look for a particular address in the memory RAM. And then it will go inside this next part of it, and then probably read the data to use. So let me see the data. So as time goes, you can see these instructions will become many, because we need to tell the computer, for instance, okay, go inside this address. Okay, the next instruction, which should be probably 0, 0, 0. Okay, I should have used actually first, like the first one 0, 0, 0, 0, and the next one 0, 0, 0, 1, and 0, 0, 1, 0. So that's 0, 1, 2. Okay, so based on each instructions, the computer knows what to do. Each instruction actually goes to a particular circuit that determines a function that the CPU should execute. And then when we are doing that, as time goes, the developer, the engineers saw that it is very hard to keep these numbers. So why don't we actually, on our papers, try to name these numbers? So let's give them names so that it will be easy. But we know that every time we need to enter that in a computer, we have to enter these particular numbers, but not these names we are giving them. And those names are called the mnemonics. So it's a funny word, mnemonics. So let's say, for instance, for this one, we can call it, let me call it alt, just like that. So whenever it sees this instruction, just stop whatever you are doing. Whenever you see this instruction, probably do just the addition. Okay, so I will call it add. Whenever you see this one, do the multiplication or subtraction. So I will call it sub. Okay, so from binary numbers, we ended up with meaningful words that can be used. So we can use these meaningful words now to program. So I could probably say, okay, add. Okay, when I say add, and I'll tell him, okay, I'll give it what to add. So let's say whatever is in the accumulator, add it to the value to that is located in address probably 1 of the memory RAM. So locate the address 1 in the memory RAM and find the data that is inside the address and add it to the value that is already in the accumulator, and probably save it back inside the memory somewhere. So that's how assembly language is born. That's assembly. Basically, that's all about assembly language. So here you have the assembly language, and here you have the computer actually language. This is what is called the machine language. So machine language, okay, and then assembly, ASM. So this is the difference. So you have the machine language, usually called the how do you call it? I think there's another name. There's the object code. Okay, so this is the object code indeed, because it goes deep to the material, the object itself. So this is the object code, the assembly code, and this basically that's how the assembly code is born. And you can imagine you can't get rid of it. So microprocessors of today have so many of these instructions, millions of them. Is it up to millions? Anyway, there are so many to the extent. If you take the microprocessor like the x86 or x64. So there are so many instructions that it becomes so complex, and the program counter works in a different ways. There are so many complex and more registers to you can have, so like 14 to 20 registers in the same CPU, that data can be easily moved from one register to another so fast, so that they can save time and move instead of going straight to the memory RAM and all this. So when you have all these instructions and that are set for each CPU, and then the mnemonics that goes with it, all these instructions is what they call instruction set architecture. So for each CPU, there's an instruction set architecture that is defined, which is how the instructions are defined, and then with their mnemonics going along. So this is the instruction set architecture. Each CPU, you know, has their own instruction set, and all CPUs know assembly. They have assembly in them. So I wonder how you manage to escape from assembly, how you manage to tell yourself that assembly is an old programming language that you can do. It has its own limitations like any other programming language, and it also has its own advantage that no other programming language can beat, like speed. And in fact, assembly language is the only language that can access the input and output of any CPU directly. No other language, even C. C has to come with a different library along to access input and output. And you might ask yourself, probably if you are not that deep into it, you might ask yourself, now what is input and output right now? And these are the problems I'm talking about when it comes to programming. Honestly, when you program and you write in C, for instance, printf or scanf, what do you do? What are you doing? What are you doing by that? What does that mean actually? So these are the concerns I have when it comes to being a programmer and software engineer to some extent. There are some things you need to know why you are doing it. For instance, when you are learning C, if you are a new programmer and probably they introduce you to you somewhere, and you might tell them, no, C is so hard, how can I learn that things? I prefer Python because it's easy. It's okay. I prefer JavaScript. Yeah, it's easy. Yeah, it's okay. It's all fine. But when it gets to a point that I ask you, okay, you need to XOR some data somewhere, or probably you need to end some data somewhere. Okay, I say, oh, you need to end some data, or you need to, I don't know, note some data somewhere. You become confused. What is that? Why am I supposed to do? Why am I doing that? So you start to ask yourself, why is it important for me to do that? So these are the questions. These are the things you must know. These are the things it is important. For instance, I think in PHP we have this called standard stdin, which is used to, it is said in the documentation that it's used to read the input stream. And then we have the sd out, which is used to read the output stream. What does that mean? Good question. So these are the things I think it is important for us now to start considering what we do and as a software developer. You might tell me, no, I prefer sticking to JavaScript somewhere there. Yes, you will create websites all the time, but I'm telling you, there are some websites you might need to really get concerned in how you write your code. You can't just escape some aspect, because this is part of computing. It is just part of computing. As far as what you are doing uses computers, you can't ignore some aspects of computer at some level. There's nothing you can do about it. You just have to consider. When security and reliability of your software becomes critical, there's nothing you can do about it. You just have to come back to those things and try to understand them. So I would prefer, if you are a software developer, that you go back and give a look, give a try to this aspect of this computing. Try to understand at least why you have this. So you can imagine later on these mnemonics are converted into something different. So whatever you write as a software actually gets converted into this and then into that. No matter the language you use, no matter either interpreted programming language or compiled or low level or high level, whatever it is, from your programming language, which is your high level programming language, it goes back to assembly. From assembly, it will go back to machine code. There's nothing you can do about it. And if you've written C, sometimes you can see that at some point your programs are compiled into .o, this .object, and I was telling you about it. So this is the object code actually. So you see, I think this is just a summary so far of what I have been through. So you can see the hardware actually took a bit of my time in trying to understand this, especially how these mnemonics are born. Honestly, it's still a dark aspect of it, and I think it requires a big understanding, a deep understanding of how the CPUs, the memory is designed. So it is important. I will still continue to be on this quest. I'll still continue to search deeper. I'll probably try some electronics. So what I realize now is I can't stay into computer engineering for long. I definitely have to come back to software development because it's kind of easy for me based on where I am in Africa here. I don't think I'll have any place in this whole Africa where I can go and will be designing CPUs. There's no place. There's no place. So I really don't want to waste too much time on electronic design of CPUs and all this. What I would like to do is give it a try. I'll give it a try. I'll try to build this little person here so that I can actually experiment this particular thing deeply by myself. So if I can get to build the clock, the addition, the arithmetic logic unit, the program counter, and get some kind of small CPU that does this small thing, so that I can see really how the CPU does this calculation. I think this should be enough. From there, I can come back to these low-level programming languages such as C, and I don't know. Should I do the COBOL and Fortran? It will depend on the time. But I would like to explore those programming languages and see how they actually do things. But I'll certainly learn assembly and go deeper, because today it is so considered that if you are writing operating systems, assembly, you can't escape it at some point. There are some things that can only be done with assembly, especially if you want to gain in speed. So I think it is cool. It's cool. So guys, this is what I've been up to when it comes to this channel goal, which is computer engineering student. I hope you are also a computer engineering student and you are ready to go deeper and also try to understand what it is. And talking of the computer engineering and why I've made it from software engineering. Software engineering, I think once we are good with the hardware, we know how the computer works and we know why we are programming, then we start to focus on how do we design good computer program, how do we design efficient computer program, and how do we organize our code bases based on the sizes of projects and all this. And this whole entire activity is part of what is called software engineering. So you can see from computer engineering, which is the design and the planning or whatever, the organization of the computer, to the design and organization of the software on the computer. So there are two fields, and as I was mentioning, I am going to move back from hardware, which is the computer designing itself, to software designing later on, after I finish understanding what hardware is deeply. So I hope this also gives you a small light, and I didn't give up, although I'm kind of posting other videos on this channel concerning the other topics, but it's my daily thing. I told you this channel is just nothing really well organized. I'm just going to throw whatever I have in mind until we really come up with something well organized, and maybe we start a bigger, a sharper channel. And I hope to have you by then. Thank you very much for watching, and see you. And please don't forget to subscribe. I usually say this at the end, and most people might not watch to the end, but please, if you get to this point right now, try to subscribe, try to tell your friends, share with them. It's nothing much. That's all I require from you. Thank you very much for watching, and see you next time.